All right, so I'll get started. So I introduced the concept of standard angle, right? So the standard angle is essentially measured from what? From like the positive x-axis sweeping over to whatever ray we're describing the angle of, you know? So let me just say it again. So the initial ray, by default, when we're talking about standard angle, is on the positive x-axis, right? And then we're sweeping over to something, and the terminal ray, wherever it is, we sweep in a counterclockwise fashion. That counts as positive standard angle, right? Now, I typically use theta. I think your book uses t because they're lazy and they didn't want to type in theta. That's my guess. It's unfortunate. When I printed the book out in like 2 pages per page, the t did not survive well in the printing. And the t and the t prime, they're hard to discern. So I would say if you're printing 2 pages to a page, it might not be a good idea. It's going to lead to confusion. At least it did for me in my reading on the fly. But then again, my eyes are not great compared to yours probably. So anyway, that's standard angle. And what did we say? We said, just to recap, we have quadrant 1, right? We have quadrant 2. We have quadrant 3. And we have quadrant 4. And if I had to describe the angles here, we have 0, less than theta, less than 90 degrees in here, right? We have 90 degrees, less than theta, less than 180 degrees here, right? And we have 180 degrees, less than theta, less than 270 degrees in quadrant 3, right? And what else do we have? We have 270 degrees, less than theta, less than 360 degrees over here, right? So that's one way you can describe standard angle, right? But there are other choices, right? Like, what's another way to describe, let me just talk a little bit about alternative descriptions. And this goes to do, the book uses the term, I think coterminal. Angles are coterminal, is that right? So for quadrant 4, for example, we could, instead of saying 270 degrees to 360 degrees, we could also say that's like minus 90 degrees to 0, right? Because you could think about this quadrant 4 as sweeping from 0 down to minus 90, right? Because that's going clockwise, so it goes negative. So we have that choice. So some people will use basically from minus 180 degrees to 180 degrees to describe the angles. So you just use negative angles for quadrants 3 and 4, or you use positive angles for quadrants 1 and 2. I mean, you have these choices. Let's just do an example. Just to try to talk a little bit about this issue. If theta is equal to 500 degrees, then give 2 other I believe the word's coterminal. I'm trying to use the language in your book. Yeah, coterminal angles. So coterminal angles, they're angles that, give you rays that are pointing in the same direction. Let's see here. So like 500 degrees, where is that? It's 140? Now, how did you get, he said 140. What did you do?
500 minus 360.
Yeah, so 500 minus 360 gives a coterminal angle, right? to the 500 degrees. Now 500 minus 360, what do you say, it was 140? 140 is in here. So it's like 90 degrees, and then we go another 50. So it's kind of sort of more or less here, right? So this right here would be 140 degrees, right? So how would you draw 500 degrees? Right, it's kind of a pain. You got to do something like this, right? Like goes all the way around like that, right? So there's a picture of 500 degrees. So 140 degrees is a coterminal angle. Can you give me another one? How about could you give me one that's negative? Negative 220. How did you get negative 220? So 500, what'd you say? 3. Oh, you just, 3, 6. I didn't track what you said. What did you say?
So you see how the coterminal angle would be 140, right?
Yeah.
So to go the other way around, you have to do
Oh, okay. So you're just like looking at it, and you see that if there's 360 total degrees all the way around, and you want it to go negative from the positive x-axis, you just sweep 220 this way, because there has to be 360 degrees all the way around. So your point is like this is also a coterminal angle, theta equal to, what did you say? Minus 220, right? Minus because it's going clockwise. Now, the mathematics here is really pretty simple. If you want to find all coterminal angles, just take one of them, right? And you subtract or add multiples of 360. That gives you all possible coterminal angles. So this is how you find coterminal angles. Either subtract or add multiples of 360. Okay? All right. So now I need to turn the page and talk about radians. All right? So what is a radian? Talking about what? Just say again. I'm sorry.
Are you talking about in reference to the unit circle, the radians that we use in the unit circle?
Reference to the unit circle? Well, that is one thing we could do, but it's a more general concept than that, right? So here's the idea of a radian. If we have two rays, let's say this one and this one, right? And you want to measure the angle that goes from one ray to the other, right? Like this. What you do to measure the number of radians is, well, yeah, you could draw a unit circle if you like. You could draw a circle of radius 2. It doesn't really matter. You just think about some circle, all right? And again, we could make that a unit circle if you'd like. But you draw some circle, all right? And so this is theta in radians. And here's the deal. Theta is defined to be, all right, it's the length of the arc, this arc length right here. I'll kind of shade it. So you know what the length of an arc is, right? If you took a piece of string and just laid it along this arc, that would be the arc length, right? Whatever that is. We usually use an S for that. All right? So it's the arc length divided by the radius, right? Which is this length right here. I'll use little r. So S over little r, that gives you the radians, the radian measure of the angle going from this initial ray to this final terminal ray. So that's pretty, it's a different way, and so we usually write, so I write the little upper circle for degrees, right? Or you can also write it out. An alternative thing, notation-wise, is you could say 500 degrees, or you could also write like 500 degree like that, you know? And, okay, so this is, I think this is actually closer to a definition of angle. Like my definition of degrees was pretty sketchy if you really look at it. And truth of the matter is this isn't great either. The best definition of angle we'll find much later in the course when we talk about something called vectors, like the last couple weeks of class actually. That's where we actually get an honest to goodness definition of angle. But that's not going to stop us from using them the whole semester, right? I mean, you guys, it's intuitive understanding what an angle is, right? You kind of know it when you see it. Like this is kind of close to 90 degrees, this one, right? So let's try to get a sense of radians. So one of the things we know is what? What's the definition? Well, let me not say the definition. How many radians are there for a whole circle, right? So let me erase this here. So for the arc length for a whole circle is called the circumference, right? So that would be 2 pi times the radius, right? So 2 pi times the radius is the circumference of the circle. So how many radians for a whole circle? So the total all the way around, 2 pi r divided by r, which is what? 2 pi, right? So there are 2 pi radians in a full revolution. Okay? So I can go back to my quadrants 1, 2, 3, 4 picture, and I can describe radian measure. I can describe the standard angle in terms of radians instead of degrees, right? So like 0 to 90 is alternatively described as 0 less than theta less than what? Pi over 2. What'd I do? Total. Like all the way around. Now, well, I'm going to keep writing here, and then I want to point out to you that there's kind of a problem with the notation, but it's, I don't know, well, I don't know if it's really a problem. All right, so pi over 2. The question is, should I use the same letter for theta in degrees and for theta in radians? Right? If you want, you could call one like theta sub d for degrees and the other one theta sub r for radians, but I'm just going to use theta for both with the understanding that if we write radians, we're using radian measure, and if we write degrees, we're using degree measure, right? And of course they're not equal, right? 90 degrees, 90 is not equal to pi over 2. But I would argue that 90 degrees is equal to pi over 2 radians. All right, that's a little, some people would say that, like there are people who argue like that's not logical. But I think it has good meaning if we apply it. I'm gonna apply that idea to change degrees to radians here in about 3 minutes, okay? Let me just finish giving this account. So pi over 2, the positive y-axis is pi over 2, right? Let me do the axes in blue. I'd use green, but that's a bad choice here. So like pi over 2 is this guy. This is pi, right? 0's here. And down here, 3 pi over 2. So you have pi over 2 less than theta less than pi in quadrant 2. In quadrant 3, you have pi less than theta less than 3 pi over 2. And finally, in quadrant 4, you have, 3 pi over 2 less than theta less than 2 pi. All right. I'm just trying to give you a sense of the lay of the land, right? Now, what if you want to find, what if you have an angle described in radians and you want to find angles which are coterminal to that? How would that go? Well, instead of adding multiples of 360, you'd add or subtract multiples of 2 pi, because 2 pi is like 360 in the world of radians, right? We'll get back to that. Let me show you some examples. Let's see here. So again, if all the way to the positive y-axis is pi over 2, what's halfway? What's this angle? In radians. Well, in degrees, what is it? It's 45 degrees, right? What is it in terms of radians? So I heard pi over 4. Yeah. Now, what's your name?
Cason.
So, what's again?
Cason, C-A-S.
Cason. So Cason already has a very well-developed intuition about angles, right? And I know not everyone here does yet. So I want to go through the logic of converting 45 degrees to pi over 4 to show you how you could do that, all right? The key idea is just that 2 pi radians is equal to 360 degrees, right? So if we start with theta equal to 45 degrees, and we want to convert to radians, what we can do, what's this say? This says that 1 is equal to 2 pi radians divided by 360 degrees, right? Now, can you simplify 2 pi radians over 360 degrees? Like if you've been taught unit conversion before, you were probably not taught to multiply by 2 pi over 360, right? Because why multiply by 2 pi over 360, which would take like 3 calculator steps, right? When you could just multiply by pi radians over 180, right? So you just cancel the 2, right? And so we do 45 degrees times pi radians over 180 degrees. So what happens here is the degree units cancel, and it leaves you with radians, right? And what is, how many times, 180 is actually 4 times 45, right? So 45 over 180 just gives you 1/4. And so there you have it, pi over 4 radians. But one of your goals in this class is to be able to think both in terms of degrees and also radians. Now, my default in terms of geometry is degrees, because I was taught degrees as a physics student, general physics student for like a while. And then later I learned about radians in my math class, and trigonometry class. But it's not a big deal. When somebody tells me pi over 4 radians, I immediately know that that's 45 degrees, right? Another example. Let's see here. What if we had 30 degrees? All right. So convert that to radians, right? So we do theta is 30 degrees times what? Times pi radians over 180 degrees. So what's 30 over 180? Well, that's 1/6. Yeah. So we get pi over 6 radians. All right? Any questions so far? Okay. Now, so of course you can do you can talk about physics, well, really kinematics, if you will, the study of motion with respect to angles, right? You can talk about you have some problems that are about like the angular speed. You guys ever study that in like high school physics or anything? A little bit. Somebody just talk about that briefly. which kind of angle measure is most natural to talk about speed? Like, I mean, this is already kind of, this is the relation, right? See this? S equals to r theta. This describes the linear distance you go along a circular arc as it relates to the radius and the angle, right? And lost my track. There we go. So you can also then look at, if you look at like the your book doesn't use change, but I'm going to use change here just to keep the distinction clear. If you look at the arc length subtended over a particular time, so this is just the change in arc length over the change in time, that would give you the average linear speed along the circular path. And if that's a circular path, that's going to be equal to r times the change in theta over the change in t. So this is what's called linear speed. And this is what's called angular speed. Now, I think your book, instead of using change in theta over change in t, it just uses like theta over t. All right. There's no like delta change notation in the book, but I'm just, it helps me to explain what I'm talking about. Let's just do an example with some numbers in it. Try to make that a little bit less mystical. So here's my question. What is the angular speed of the seconds hand on a clock? Do you guys know what I mean by the seconds hand? So if you think about a clock, right? It starts here, right? And then tick, 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 tick. So I'm ignoring the jumpiness of the motion. I just want to think about it as like a smooth, well, imagine you have imagine you have a clock which doesn't jump. It just kind of continuously, smoothly goes around, right? So if it starts and it goes one full revolution, so let's think about one revolution. So how many, I'm going to use that to figure out, and by the way, the symbol we use for linear speed is v. The symbol we use for angular speed is this omega. One of the things I should be doing in here is teaching you some Greek, right? So we've already been using theta, that's a Greek letter, which is kind of like Greek for t, which is why your book is using t. Omega is, well, there's omega. This is lowercase omega. You may have seen capital omega. That's this guy, right, for ohms in physics. But lowercase omega is what we tend to use for angular speed. And the units for omega should be radians per second. I mean, that's one choice. You could use, those are natural units. Okay, so omega, so we have omega is going to be equal to the change in theta over the change in time, and we're thinking about it being a uniform rate of change. So you can pick any particular sweep that you want. I'm saying look at the whole sweep, right? So what's the change in theta if we go all the way around? It's 2 pi, right? 2 pi radians is a full revolution. And how much time does it take for the second? What's that? 60 seconds, right? So what is that then? Well, I need a calculator. You're like, well, it's pi over 30 radians per second, right? That's a good mathematician's answer. Let's give an engineer's answer. Let's give a decimal, yeah? So 2 times pi divided by 60, what do I got? stupid. This thing gives you back pi over 30. It's such a smart aleck. If you hit the S to D, that's the decimal, so 0.1047. Radians per second. So there you go, that's the angular speed. What are other popular units that people use for radians, for like angular speed, descriptions of it? Like, I think the most common one would be revolutions per minute, or RPM. You ever heard, I mean, if you have a tool, you might have a drill that does 30,000 RPM, right? How would you convert revolutions per minute to radians per second, or vice versa? Like, what is the angular speed here in terms of revolutions per minute? So revolutions per minute, notice algebraically this would be a revolution over a minute, right? So how can we convert? So I'll start down here, omega 0.1047 radians per second. And I want to multiply by unit conversion factors. So like, how do I change a radian to a revolution? What's the relation between radians and revolution? Yeah, I said 360 degrees equals to 2 pi radians equals to what? 1 revolution. This is the relation between revolutions and radians and degrees. So to convert from radians to revolutions, I can use the fact that a revolution divided by 2 pi radians is equal to what? It's equal to the number 1, right? If I divide by 2 pi radians, I get 1 is equal to revolution over 2 pi radian. So if I want to convert radians to revolutions, I should multiply by that, because then the radians will cancel. So I multiply, because that's just multiplying by 1, right? So multiply by revolution, revolution divided by 2 pi radians. Now that's going to give me what? If I just multiplied by that, I'd have what? I'd have like revolutions per second. Now how do I convert seconds to minutes? Would what?
Would you multiply by 60?
Multiply by 60. Now remember, when I have a quantity, the only thing I'm allowed to do to that is add 0 or multiply by 1. So like, how are minutes and seconds related is my question. You might be right, multiply by 60, but I want us to understand. Let's see here. So what you do, check?
Sure.
But how are minutes and seconds related?
60 seconds.
Yeah, 60 seconds is equal to 1 minute, right? So this means that a minute, rather 60 seconds, you got to be careful here. If I'm not careful, I'll get the wrong kind of number 1 to multiply here. But 60 seconds over 1 minute, that's 1, right? So I can multiply by that factor. Right? And now I should see what? I should see that seconds cancel, radians cancel, and I'm left with revolution per minute and whatever number that is, right? So I get out my handy-dandy calculator. What do I get? So what you said was right. You just multiply by 60. I wanted to explain,
Multiply omega by 60.
Well, yeah, I'm multiplying 0.0147. I think if I left it in terms of radians, it would be easier. Like if I hadn't used this number here, if I just kept the 2 pi over 60, it would be even easier to see, right? Let me sort of undo my numerics for a second here. This was what? 2 pi over 60, right? What happens? the 2 pi's cancel. The 60s cancel. And what do we get? 1. 1 revolution per minute. Which the standard nomenclature is RPM, right? And this is completely unsurprising if you just take a step back and think about the problem. How many revolutions per minute does the second hand on a clock make? 1. Yeah, this makes sense. But I wanted to go through this as an exercise on how to change units, because I've assigned you guys some homework which touches on unit conversion, so I'm not going to belabor this point. I want to shift gears now and talk about sine and cosine, all right? The other thing I should mention is there are some problems in the homework about like area subtended by an arc. So we should talk a little bit about that. I'll be brief. I just tell you the formula. I won't even work an example today. But what would the area of this sector be? So how about this? For the whole area for the whole circle, you know, the really area for the disk, right? The filled in circle, if you will. We know that that's pi r squared, right? So to figure out the area of a sector, you need to multiply by like the portion, the fraction of the circle which is described by that sector, right? So to get the fraction, I just take theta and divide by 2 pi. That tells me the amount of radians, like the fraction of radians that's subtended by the arc. So like I do theta divided by 2 pi, that gives me the fraction of the circle which is given by this arc. And then I just multiply by the whole area, which is pi r squared, right? And what's that give you? The pi's cancel, right? And so you get the formula, area is equal to 1/2 theta r squared. This is the area for a piece of pie in terms of radians, all right? It's just, all the formula is saying is the area of a sector, it's just the fraction of the total area of the circle, because we know the total area is pi r squared, so. If you put theta equals to 2 pi, what happens here? You get pi r squared, right? So you can always check this formula with the whole thing. But anyway, that's the formula for area of a sector. Now, it's important to notice that the formula for arc length and the formula for area, they're both in terms of radian measure. If you just try to use these formulas with degrees, they don't make sense. If you have a problem with degrees and you're asked a question about area, right, or if you're asked a question about arc length, what you have to do is you have to take the degrees and you have to convert them to radians before you try to crunch the numbers, all right? So there's some homework that is based on that idea. All right. The unit circle. Cosine and sine. So the unit circle. By unit circle, we mean radius 1, right? So we imagined it's centered at the origin. The radius is 1, right? So you can already tell me some special points on this circle, right? They're really easy to find. For example, this one, what's that point? 0, well, heart's in the right place, but actually, you need to like flip your heart over. I don't know, what's the right analogy? 1, 0, right? This is 1, 0. X then Y. And then up here, that's the one you're thinking about, 0, 1, right? Okay, so, and what's the equation of the circle? X squared plus y squared equals to 1. Very good. This is the equation of the unit circle. All right? So we can define sine and cosine of an angle as follows. So you pick a point on the unit circle, all right? And that is that standard angle theta, right? And we define cosine of theta to be the x component, x coordinate of the point, and sine of theta to be the y coordinate of the point. So the points on the unit circle define the values of cosine and sine in this way. So some like really simple stuff. What would cosine of 0 be? What would sine of 0 be? So like 1, 0 is what? It is cosine of 0, sine of 0, right? Because what? Because that's where 0 radians is, right? This is cosine and sine in radians. Well, excuse me. Actually, you could go either way, right? We could think about the unit circle in terms of degrees, or we could think about it in terms of radians. You do have these choices. We will do both. All right? And the good news is I didn't really have to make a decision because 0 degrees is equal to 0 radians. So like, I don't know. Anyway, it's funny. So cosine of 0 is what? Right, so this tells me cosine of 0 is 1. Sine of 0 is what? 0. Now look at this point up here. What's that tell me about sine and cosine? So this up here is theta equal to what? Pi over 2 if you like, or you could say pi over 2 radians. Now, incidentally, it is our custom if we don't write degrees, it's understood to be radians, right? That's the custom. I've been writing radians to emphasize what I'm doing, but technically speaking, I don't have to. I think it's actually really helpful in terms of, especially if you're doing, I would encourage you to write them if you're thinking about a unit conversion problem. Actually writing the radians is helpful because it keeps you accountable to cancel them in the right way, all right? But it is commonplace to not write, like just write theta equals pi over 2. But if I was going to be less lazy, I would say pi over 2 radians, right? I'll say 90 degrees here just to mix it up a bit. So what's the cosine? I've worked myself into a anyway, here, cosine of 90 degrees is what? Yeah. 0, right? And sine of 90 degrees is 1. Yeah. Now, I do have to admit, we're using, like the notation here is a little bit dangerous in the sense that there are different functions for degrees and radians. Cosine in degrees and cosine in radians are different functions. If you feed the number 3 excuse me, if you feed the number, yeah, let's say about the number 3 into the degree function for cosine of 3 degrees is really, really close to like close to 1. Because where's 3 degrees? It's like right here, right? So cosine of, if you think about this point, the x component's really close to 1. It's like cosine of 3 degrees. It's very close to 1. What's cosine of 3 radians? Well, 3 radians, it's like over here. All right, because pi radians, pi is 3.14, so 3 radians is like essentially diametrically opposed to that point. So cosine in radians of 3 is about -1. So whether or not you're thinking of cosine as taking in a radian or taking in a degree will make a big difference. And your calculator is not clairvoyant. It does not know whether that 3 that you feed it is radians or degrees, right? So whatever your calculator is in, if it's in degree mode, it's going to use cosine in degrees, right? If it's in radian mode, it's going to do cosine in radians. But we're going to write cosine for both of those as if they're the same function. So it is, technically speaking, yeah, it's confusing. But this is why in calculus, we always use radians, because we always want to be talking about the cosine and radians function. Like the derivative of the cosine and radian function is minus sine. The derivative of sine in radians is cosine. If you use the degree functions, like the derivatives involve these factors, like 180 factors everywhere. So like calculus is much more cluttered if you use degree functions. That's why we use radians in calculus. They're more natural. All right, anyway. I actually don't think you guys are going to get confused about this. I just wanted to make you aware of the issue. We have to keep track of whether we're using radians or degrees. Let me start this again. Let's talk about my previous circle was better, I think. This one, something happened. So this would be like pi over 4, right? Radians. And so what would this point be here on the unit circle? Because I'd like to figure out what is the cosine of pi over 4 and what's the sine of pi over 4. We can figure it out with analytic geometry, right? So this line is y equals to x, right? Because it's the slope 1 line. That's the one that's going to cut the circle in the middle. I just argue you can see this by symmetry, right? And so if that's where y equals x intersects this, how do you find the specific point? Well, you plug that equation into this equation. That's how you find points of intersection, right? So this would give us x squared plus x squared equals to 1, which gives us 2x squared equals to 1, which gives us x squared is 1/2. What does that tell us? X is equal to what? Plus or minus 1 over the square root of 2. Why is there a minus solution? It's picking up this one over here too, isn't it? There's 2 points of intersection. That's why the algebra did that. Now, our context is in quadrant 1, so we know x is positive there, right? And so, hey, apparently, cosine pi over 4 is what? 1 over the square root of 2. We just worked it out. What's the sine of pi over 4? So check this out. If this generic point is cosine theta, sine theta, all right, what's the relation of sine and cosine? Right? The cosine is x. The sine is y. X squared plus y squared equals to 1. What does that mean about sine and cosine? See this? They have to satisfy that because they're on the circle. That means we have the identity cosine squared theta plus sine squared theta is equal to 1. The so-called Pythagorean identity for sine and cosine. Do you guys know what I mean? There's a notation I'm using. This is used throughout calculus. When I write cosine squared theta, this is a shorthand for cosine of theta quantity squared, okay? That's what that notation means here. You have a question?
You say you got 1 over the 2 right here.
Yeah. Because I got to choose the positive solution because I'm up here. Right, this point right here is cosine pi over 4, sine pi over 4, right?
I didn't prepare my calculator.
So I didn't plug it into the calculator. Like, I'm seeing that it's 1 over root 2 because that's what x works out to on the unit circle at that point. And once you know that, you can use this to figure out what sine is, right? What is if you know sine, what's cosine? Excuse me, if you know cosine, what's sine? So if cosine squared theta plus sine squared theta is equal to 1, then sine squared theta is equal to 1 minus cosine squared theta, right? And we can take the square root of both sides. But remember, when we take a square root like that, we have to allow for plus or minus. Am I over time? I mean, yeah. So sine theta is plus or minus the square root of 1 minus cosine squared theta, right? Now, whether you're going to choose plus or minus, it depends on where you are, right? Think about the sectors. Cosine is positive in sectors 1 and 4. Cosine is negative in sectors 2 and 3. Likewise, sine is positive in sectors 1 and 2, and sine is negative in sectors 4 and 3. Right. We'll talk more about this. But just to finish this example, what's the sine of pi over 4? Well, I mean, I'm being dumb. We don't actually need to use that here. There's an easier, a lazier way to find sine of pi over 4. What is it? Y is equal to x, right? Duh. This is the line y equals x. So what's the y coordinate at that point? It's the same as the x coordinate. So the sine of pi over 4 is also equal to 1 over root 2. All right, so to let you know where we're going, next time we're going to talk about how we can use the unit circle and the standard values. So the standard angles are pi over 6, pi over 4, pi over 3. And we'll learn how we can use those standard angles to calculate sine and cosine around the unit circle using that reference angle idea I talked about last time. So we're going to get back to that again. But anyway, thanks, guys. I'll stop here.